In this tutorial, we're going to model a theoretical world where there's no friction and no energy loss. In this ideal world, let's say that we have some mass sitting at rest on a frictionless horizontal surface. That mass is attached to a spring, which is fixed to a wall. The center of the mass is resting at 0 along the x-axis, which is also known as the equilibrium position. If we pull the mass to the right at a distance of x, then the position at the center of the mass is positive x. If we push the mass to the left at a distance of x, then the position at the center of the mass is negative x. Now, let's say we pull the mass to position x to the right, and then we release the mass. What happens to the mass? Well, the mass will spring back to the left until the center of the mass reaches the equilibrium position. But it won't stop there. The mass will continue moving to the left, and then eventually come to a stop. But it won't stop for long. The mass will then begin moving to the right, passing the equilibrium position again, until stopping at the initial release point, located at x distance to the right of the equilibrium position. The mass will then begin its journey again, moving back and forth along the horizontal surface. And because this is an ideal world where there's no friction and no energy loss, this mass will move back and forth forever. This infinite back and forth cycle is an example of simple harmonic motion. Using differential equations, you can predict the position, velocity, and acceleration of the mass at any time t. How can we use the differential equations.jl package to solve these types of problems in Julia? Well, let's find out. Welcome to Doggo.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. I'm assuming that you've watched the first 6 episodes of this series, so I'm assuming that you know how to use Pluto notebooks and that you know the basics of the Julia programming language. I'm also assuming that you know how to use the differential equations.jl package in order to solve both first-order ordinary differential equations and second-order ordinary differential equations. With that said, let's get started. Let's start by firing up the Julia REPL and launching Pluto. Next, let's create a new notebook and title it Simple Harmonic Motion. This is optional, but I'm going to customize this user interface like I did in the first tutorial. Let's save this file by using the Save Notebook bar at the top. Just as a reference, I'm going to add a link to the Wikipedia article on simple harmonic motion. Next, let's add a few packages. Now that everything's loaded, let's describe the problem that we're trying to solve. Just like the projectile motion problem, the simple harmonic motion problem is an example of a second-order ordinary differential equation. In order to solve the simple harmonic motion problem, the first thing we need to know is Hooke's law. So, what is this equation? Hooke's law is named after Robert Hooke, who was a 17th century British physicist. Here's a fun fact. Robert Hooke was the first person to visualize a microorganism using a microscope. But Hooke's law doesn't have anything to do with microscopes or microorganisms. Hooke's law has to do with springs. This law states that the force F needed to extend or compress a spring by some distance x scales linearly with respect to that distance. So going back to the equation, F sub s is the spring force. K is a positive number, which is also known as the spring constant. This number is different for every spring. The weaker the spring, the lower the constant K. The stronger the spring, the higher the constant K. X is the displacement, or location of the center of the mass that is attached to the spring. When the mass is at rest, x is equal to 0. A positive number indicates that the center of the mass is to the right of the equilibrium position. A negative number indicates that the center of the mass is to the left of the equilibrium position. The minus sign in front of the k times x means that the spring force is attempting to restore the spring back to the equilibrium position. So when x is positive, the force is negative. When x is negative, the force is positive. Now, these are all static measurements, so this equation doesn't provide any information about the motion of a mass attached to that spring. For that, we need Newton's second law of motion. According to the Wikipedia article on Isaac Newton, quote, Sir Isaac Newton was an English mathematician, physicist, astronomer, alchemist, theologian, and author, widely recognized as one of the greatest mathematicians and physicists, and among the most influential scientists of all time. Unquote. No doubt you've heard of Sir Isaac Newton, but you may not have heard about Robert Hooke. Here's another fun fact. Hooke and Newton were contemporaries and intellectual rivals in England during the 1600s. Hooke had been studying gravitation for years before Newton published his now famous book on the subject in 1687. Hooke confronted Newton about this and demanded that Hooke be given credit for giving Newton the ideas that led to the law of universal gravitation. But Newton refused. Other than this being a spicy tidbit of historical tea, I think the lesson here is that not much has changed during the past several hundred years when it comes to the cutthroat world of competitive academia. In any event, according to the Wikipedia article on the subject, quote, Newton's laws of motion are three basic laws of classical mechanics that describe the relationship between the motion of an object and the forces acting on it. Unquote. Newton's second law of motion is expressed by the equation F equals ma, or m times a, where F is the force, and m is the mass, and a is the acceleration. We know from the last tutorial that acceleration is the second derivative of position with respect to time. Knowing this, we can now combine the equations to create a second-order ordinary differential equation whose solution will allow us to predict the position, velocity, and acceleration at any time t of a mass in motion that is attached to a fixed spring. So this final equation states that the second derivative of position with respect to time is equal to negative k over m times x, where k is the spring constant, m is the mass, and x is the position. So this is the second order ordinary differential equation that we need to solve. As we learned in the last tutorial, the differentialequations.jl package expects second order ODEs to be a Julia function that takes the arguments du, u, p, and t. The equation for the simple harmonic motion problem contains two parameters, k and m. It can get a little confusing referring to the parameters as p1 and p2, so let's apply the skills that we learned in a previous tutorial so we can use the actual equation in our Julia function. Now that we've defined our Julia function, let's assign values to our variables. du is the velocity in meters per second. In this case, du is the same as dx. All we need for dx is the initial value. For this demonstration, let's assume that we pull the center of mass to some displacement x, and then release it starting with an initial velocity of 0. U is the position in meters. In this case, u is the same as x. Again, all we need for x is the initial value, which is the initial displacement. Let's bind this variable to a slider so we can change this value later. A positive number is displacement to the right, and a negative number is displacement to the left. This slider will allow us to set the initial displacement anywhere from 25 centimeters to the right to 25 centimeters to the left. For p, we need to assign values for two parameters, the spring constant k and the mass m. The unit of measure for the spring constant k is newtons per meter. There's a wide range of values for the spring constant, starting at the low end for toy springs, and going up to the high end, like for the wheel suspension in trucks and trains. For this demonstration, let's bind the variable k to a slider, using values towards the lower end of the range for spring constants. M is the mass of the object in kilograms. Let's bind the variable m to a slider so we can change this value later. For my US viewers, 1 kilogram is about 2.2 pounds. Now that we've assigned values for both k and m, we need to place them inside of a vector assigned to the variable p. Next, we need to assign values for t, which in this example is time in seconds. Let's bind the variable for the ending time to a slider that will give us a time span between 0 and 20 seconds. Okay, now that we've assigned the variables, we need to define the problem that we're trying to solve. This is the same function that we used in the last tutorial, but in this case, we need to include the argument p since we have a couple of parameters. Okay, now that we've defined the problem, let's solve it. As with previous examples, in order to solve this problem, all you need to do is use the solve function. Okay, let's take a look at this solution. The value 1 column is for du, which in this case is the velocity in meters per second. A negative value means that our mass is moving to the left. A positive value means that our mass is moving to the right. The value 2 column is for u, which in this case is the position in meters. A positive value means that the center of our mass is located to the right of the equilibrium position, or 0. A negative value means that the center of our mass is located to the left of the equilibrium position. So at timestamp 0, the center of our mass has been pulled 25 centimeters to the right of the equilibrium position, and it has a velocity of 0 since it hasn't been released yet. At the next timestamp, the mass has been released, so the mass has moved slightly to the left, and we can see that the velocity is now a negative number, meaning that the mass has started moving to the left. At some point, we see the center of the mass cross the equilibrium position, but the velocity is still negative at that point, so the mass is still moving to the left, but it's starting to slow down. At some point, we see the velocity of the mass slow down to 0, meaning that it stopped moving. But then it immediately starts moving to the right. We've only modeled 20 seconds, but this back and forth movement goes on forever. And this is what simple harmonic motion is all about. Let's set up some variables so we can track position, velocity, and acceleration for any time t. Okay, let's plot the solution to see what it looks like. Surprise! The solution is a sine wave and a cosine wave. Let's start with the orange curve. This curve shows the position at any time t. Notice that it starts at 0.25, which is the initial displacement. As soon as the mass is released, the mass moves towards 0, and then ends up at negative 0.25. Once it reaches that point, the mass moves back towards 0, and then ends up at the starting point of positive 0.25. From there, the pattern repeats. This blue curve shows the velocity at any time t. Notice that it starts at 0, since the mass isn't moving at the initial position. But as soon as the mass is released, the velocity turns negative, meaning that the mass is moving to the left. Notice that the mass reaches its maximum velocity when the position is 0, meaning that the mass is moving the fastest as the center of mass is crossing the equilibrium position. The values are still negative after the center of mass crosses the equilibrium position, but you can see that it's starting to slow down. In fact, the velocity reaches 0 when the position reaches negative 0.25, which is the maximum position to the left of the equilibrium position. Immediately after reaching the maximum position to the left, the velocity turns positive, meaning that the mass begins moving to the right until the mass gets back to the initial position, at which point the velocity also returns to 0. And on it goes. Let's add some attributes to our plot recipe to help clarify this plot. You may need to play around with the values for the legend placement. Okay, now that we have our plots, let's pull down our widgets so we can perform some analysis. I'm going to fast forward through this part. I'm going to show you a little life hack so we can reset our sliders while also combining the sliders into a couple of lines. We can set up a button widget to reset the sliders. Now we can use the reset variable inside any cell that contains a slider. Let's combine the time and position sliders. You can just copy and paste some of this code. In order to clear the error messages, we need to delete the original cells for the time and position sliders. Let's repeat this process for the parameter sliders. Again, in order to clear the error messages, we need to delete the original cells for the spring constant slider and for the mass slider. Let's hide some of this code. Okay, that's a lot cleaner. Let's add a markdown cell so we can see the values for position, velocity, and acceleration at any time t. Okay, that's enough life hacks for today. Let's hide the cell and then perform some analysis. When you move the time slider, you can see both the plot and the values change for any time t. Notice that at time 0, the center of the mass is located 25 centimeters to the right of the equilibrium position, and it has a velocity of 0. But at that point, it already has a negative acceleration, meaning that the spring is trying to restore itself to the left, or back to the equilibrium position. Try to move the time slider so that the position equals 0. At that point, the velocity is negative 0.25, which is the maximum velocity moving to the left. Also notice that the acceleration is now 0. Now try moving the time slider so that the position equals negative 0.25. At this point, the velocity is 0, and the acceleration is positive 0.25, meaning that the spring is trying to restore itself to the right. Now try moving the time slider until the position is back to positive 0.25. This is the time it takes our mass to complete one full cycle using this spring. The cycle time is also known as the period. Interesting, right? Let's test our reset button. Cool, right? Now let's move on to the initial position, which also happens to be the initial displacement. The absolute value of the initial displacement is the maximum position that the mass can travel to the left or to the right of the equilibrium position. This maximum distance is known as the amplitude. When you move the position slider, you can see that the shape of the curves change. Notice what happens when you move the initial position to 0. Since 0 is the equilibrium position, all of the values are 0 for position, velocity, and acceleration. You can also move the initial position to the left of the equilibrium position by selecting a negative value. Changing the spring constant value has a significant impact on the shape of the curves. By using a weaker spring, you increase the period and decrease the velocity. By using a stronger spring, you decrease the period and increase the velocity. But notice the position still moves back and forth between positive 0.25 and negative 0.25. So all you're doing by changing the spring is making the mass move slower or faster, but it has no impact on the amplitude. Let's hit the reset button again. Likewise, changing the mass has a significant impact on the shape of the curves. By using a lighter mass, you decrease the period and increase the velocity. By using a heavier mass, you increase the period and decrease the velocity. But just like before, the mass continues to move back and forth between positive 0.25 and negative 0.25, regardless of the weight of the mass. So again, all you're doing by changing the weight of the mass is making the mass move faster or slower, but it has no impact on the amplitude. And of course, you can move all of the sliders however you like. Pretty cool, right? Now, there's another type of plot that I want to show you called a phase space plot. According to the Wikipedia article on phase space, quote, "A phase space is a space in which all possible states of a system are represented, with each possible state corresponding to one unique point on that phase space. For mechanical systems, the phase space usually consists of all possible values of position and momentum." Unquote. In other words, we need a plot showing position along the x-axis and velocity along the y-axis for any time t. So that shouldn't be a problem. Let's reset our sliders and add the code for this plot. There's a link to my code in the description below. I'm not sure if this is a bug or if this is just my monitor, but when I use an aspect ratio of 1.0, I don't get a perfect square on my screen. So I'm using a value of 1.1. You may need to play around with this number. I added a semicolon at the end of this code in order to suppress the output, which is why you don't see a new plot yet. That's because we need to add a dot showing our mass by using the scatter-bang plotting function. I'm going to move the code for this plot so we can see it better. So what does this plot show us, and why is it useful? Notice there's no axis for time, so the only way we can see the impact of time is by using the time slider. Let's move the time slider to 0 to see what happens. Notice that everything disappeared, with the exception of the red dot. This red dot shows the position and velocity at time 0. The position of positive 25 centimeters is the initial displacement. Try moving the initial position slider. As you can see, you're just moving the mass back and forth horizontally. Now try moving the time slider until the position is at 0. Notice that the red dot moves clockwise. As the position of the center of the mass moves from 0.25 to 0, the velocity of the mass moves from 0 to negative 0.25, which is the maximum velocity moving to the left. Now try moving the time slider until the position is at negative 0.25. Notice that the red dot continues to move clockwise. As the position of the center of the mass moves from 0 to negative 0.25, the velocity of the mass moves from negative 0.25 to 0, meaning that the mass has completely stopped moving. Notice anything peculiar about the time? 3.15 is pretty close to pi. That can't be a coincidence. Let's put a pin in that thought, and let's keep going. As you continue to move the time slider, the red dot continues moving clockwise until it returns to its initial position. This time t is the period, or the amount of time for our mass to complete one full cycle of motion. If you continue to move the time slider, the plot simply loops over itself, so the position to velocity relationship can be found somewhere on this orbit at any time t. Interesting, right? Let's move the time slider back until we get to the time to complete one full cycle. This time of 6.29 seconds is actually 2 pi, but it's slightly off, partly due to the slider and partly due to my rounding. 2 pi radians is equal to 360 degrees, which is one complete rotation around a circle. But this number is 2 pi seconds, not radians, meaning that it takes our mass 2 pi seconds to complete one full back and forth cycle, which is the period. So this can't be a coincidence. The period must have some relationship with 2 pi. Let's move the time slider back to pi seconds. This time of 3.15 seconds is actually pi seconds, but it's slightly off, partly due to the slider and partly due to my rounding. Let's move the other sliders to see if they have any impact on the period. When you move the initial position slider, nothing happens to the period. When you change the spring constant, there's a big impact on the period. The weaker the spring, the longer the period. The stronger the spring, the shorter the period. When you change the weight of the mass, there's also a big impact on the period. But the impact is the opposite of the impact of the spring constant. The lower the weight, the shorter the period. The higher the weight, the longer the period. So, based on our observations, we can conclude that the period has some relationship with 2 pi, the spring constant, and the mass. But the period has no relationship with the initial position. Further, the period increases when mass increases, but the period decreases when the spring constant increases. So it turns out that the equation for the period is exactly that. The period is 2 pi times the square root of m over k. I used an initial setting of 1 for both m and k, so that's the reason why the period in my example was 2 pi seconds. As you can see, there is no x in this equation, so the period is completely independent of the initial position. Let's use this equation to calculate the period. Now, let's add this to our Markdown cell so we can track the period whenever we change the parameters. Pretty cool, right? And of course, you can move all of the sliders however you like. I don't know about you, but I find these models to be endlessly fascinating. I know that animations are a popular way to visualize this motion, but there's something about having the ability to interact with the model that I like. I also enjoy having the ability to build my own models so I can customize it. I hope that you're enjoying your experience as well. The simple harmonic motion problem is another example of a second order ordinary differential equation problem. Although the setup is unique to this problem, solving this problem using the differentialequations.jl package follows the same workflow as the projectile motion problem that we solved in the last tutorial. In addition to plotting the solution, we learned about a new type of plot called the phase space plot, which shows the relationship between position and velocity. I vaguely remember studying this subject in high school physics, but to be honest, I don't recall it being this fascinating. Upon reflection, I think that one of the issues that I had in high school was that I probably spent too much time simply trying to memorize the math equations, and not enough time trying to understand the physics. Now that I've been playing around with the differentialequations.jl package and with Pluto for a while, I think one of the greatest benefits of combining the differentialequations.jl package with Pluto for educational purposes is that this combination allows students to spend less time on the math and allows them to spend more time trying to understand the science. Now, I'm not saying that learning the math isn't important. I'm just saying that if you have the opportunity to supplement your education with these tools, it may help you gain greater intuition into the problems that you're trying to solve. And that can only be a good thing. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, please consider making a purchase at the Doggo.jl online store. You can browse through a wide selection of Doggo.jl merch by clicking on the Store tab. For one-time donations, please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get early access to all of my new videos. Early access videos do not contain YouTube ads. New tutorials are posted on Sundays/Mondays. Thanks for watching, and good luck on your Julia journey.